Hi everybody, welcome back to this course on Internet Technologies. I'm Vardan and today we'll be learning about variable length subnet mask and classless interdomain routing. In classic subnetting, once you decide on a subnet mask for a network, every subnet has to use the same mask, whether it needs a few hosts or 100. And this often leads to address wastage. And that is where variable length subnet masking or VLSM comes in. VLSM allows you to use different subnet masks within the same network block. You can create larger subnets for areas needing more hosts and smaller subnets where fewer addresses are enough. And this flexibility lets network admins allocate IP space much more efficiently. It also keeps routing manageable since you can still represent multiple subnets with aggregated routes if planned properly. Now, let's look at a practical problem to see why VLSM is needed. Imagine you have a class C network 192.203.17.0. Now you need to split it into three subnets, one for 110 hosts, one for 50 hosts, and one for 45 hosts. If you were using classic subnetting, your only options are masks like 255.255.255.128 for 128 hosts, 255.255.255.192 for 64, and so on. And the problem is none of these neatly fit 110, 50, and 45 hosts without wasting a lot of addresses or falling short. For example, you need to allocate 128 addresses for the 110 subnet, 110 host subnet, and other 64 address block for a 50 host subnet, wasting quite a few addresses in this process. This is where VLSM steps in and saves the day. So how do we fix this with VLSM? First, we split the 192.203.17.0 network using 255.255.255.128 mask, creating two ranges, two subnets. So one is 192.203.17.0 to 192.203.17.127, and the other is 192.203.17.128 to 192.203.17.255. So each of these can support 128 hosts, and now assigning the first block to the subnet needing 110 hosts, that's perfect. Then take the second block and split it further using a mask of 255.255.255.192, which creates two more subnets. So first is 192.203.17.128 to 192.203.17.191 for 64 hosts. Then 192.203.17.192 to 192.203.17.255, again for 64 hosts. Now you have two subnets that can handle the 50 and 45 host requirements without wasting too many addresses, and that is VLSM in action. So here's how that looks visually. First we start with 192.203.17.0 to .127 for the 110 host subnet. Then we split the second half 192.203.17.128 to .191 for 50 host. Then .192 to .255 for 45 host. Each subnet now uses a mask appropriate for its size. There's no wastage, no shortage. This is why VLSM is such a vital tool for IP network design. So as networks expanded, classful addressing quickly became impractical. The fixed structure caused significant address wastage. For example, Class A networks had over 16 million addresses each, far more than most organizations ever needed. As demand exploded, solutions like geographical IP allocation, private IP ranges combined with NAT, and most importantly, CIDR or classless interdomain routing emerged. So, CIDR abandoned rigid classes, allowing better aggregation and efficient address management, reducing wastage and preventing early exhaustion of IPv4 space. As the number of networks worldwide surged, the global routing tables saturated and routers struggled under the load, needing more memory and processing power to manage huge tables of routes. So CIDR was introduced to tackle this problem. It scrapped the old ABC class structure, and instead networks are now described as IP address slash number of network bits. For example, 144.16.192.57/18 means the first 18 bits of the address are the network portion and the rest identify the host. In binary, that becomes 18 ones followed by 14 zeros. This makes route aggregation easier and shrinks the number of entries in global routing tables, and it improves routing efficiency. So CIDR follows a few simple rules to keep things organized. The number of addresses in any block must be a power of 2, like 4, 8, 16, 32, and so on. The starting address of a block must be divisible by the number of addresses in the block. For instance, a 16 address block cannot start with 144.16.233.36 because 36 isn't a multiple of 16. It could start with .64 because 64 divided by 16 equals 4. That's a clean multiple. And these rules keep IP addresses assignment orderly and simple. So let's finish with a quick example. Take 144.16.192.24/29. The /29 means 29 bits are for the network, leaving 3 bits for the host address. Now, 2 raised to the power 3 equals 8 addresses in total. Out of those 8, 6 are usable for host. 1 is the network address itself, 1 is the broadcast address. So this range covers 144.16.192.24 to .31, and this is how CIDR gives us the flexibility to create networks of exactly the size we need, whether it's for a handful of devices or thousands. And with that, we've come to the end of this lesson. And in the next lesson, we'll learn about routing methods and routing tables. So thank you for joining in, and I'll see you next time.